Okay, so here's what we were talking about last time. We were talking about this idea of diagonalization. We actually spent a fair amount of time talking about, what does that even mean, right? There's some subtleties involved. I mean, we define this idea of similarity, which is a hard to motivate term as it's defined. But we took this other point of view then, this equivalent point of view on similarity. Again, try to avoid the inadvertent puns. They're all too easy to accidentally do. But this does give a nice motivation for the use of the term similarity. We use the term similar because these two matrices A and B have something in common. Here's what they have in common. You can see it right there. The underlying linear transformation that these two matrices represent, A and B. They both represent the same linear transformation T. This conjugation construction up there is really just a kind of a translation of how do you describe T in one language to instead how do you describe the same thing in a different language. So similarity is a very reasonable choice of words. These 82 matrices that are similar do have fundamentally something important in common with each other. Okay, that in mind, we moved on to this idea of diagonalizability. And again, the idea is you can think about this in terms of conjugations, but I like to instead think about it as pertains to change of basis. So if you can do a change of basis describing the same linear transformation, right? Let me zoom in. If describing the same linear transformation just with respect to a different basis, if the result can be made to be diagonal, then we say this is a diagonalizable matrix. In other words, said differently, this matrix that we're looking at, that that might be diagonalizable, that might have that property of being similar to a diagonal matrix. That matrix is just one way to represent the linear transformation we're really interested in. Diagonalizability says that this linear transformation, independent of how you might happen to be looking at it right now, arbitrarily, that there is a point of view on that linear transformation, there is a language with respect to which you can think about it, that where the proper description is a diagonal matrix. Right? So in some sense, a matrix that is diagonalizable is a matrix that you're just thinking of the wrong way. You're thinking of it with respect to an inconvenient basis. There is a better, more natural basis with respect to which to think about it that makes that linear transformation easier to understand, represented by a diagonal matrix. Okay. All right. So that's about where we left off. Oh, and let me comment here, why we care about diagonalizability. This is again a repetition, but we care about diagonalizability for reasons that will reveal themselves a little bit today. A little bit. Small applications today. But the big applications that we're going to see in this course will come in a few weeks. It's a little bit ways off. But it turns out I couldn't begin to suggest exactly why this is, given where we are in the course at the moment. But it turns out that this idea is really important in the question of solving a certain category of differential equations, believe it or not. And we'll fill in all those blanks when we get to it. Okay, so where we left off last time, some discussion about language. I won't repeat all of this, but remember, when we talk about putting a matrix into a form, we're talking about understanding something that's fundamentally preserved and interesting, and just changing the way in which we talk about it by a process that preserves what we're fundamentally interested in. So look again at the analogy between the row reduction process and the diagonalization process, and how they're completely different, right? But there is an analogy between them. Try to avoid thinking about that as a similarity between them. Again, inadvertent puns all over the place. Okay, so here's where we left off. We were looking at this example of this matrix that we've already studied. We know the eigenvectors and the eigenvalues. Right? That's arithmetic from section 5.4. And then, for reasons that have not yet fully revealed themselves, we decided to do something seemingly a little bit weird. We decided to take these vectors, these eigenvectors, use them to construct a basis. Okay, weird. And then ask what would happen if I try to understand the given matrix A, not with respect to the original standard basis, but what if I were to try to understand this matrix A with respect to a basis consisting of its eigenvectors? No reason to believe something particularly nice is going to happen here, but let's just see what happens. And so we made it through this calculation last time, but I want to do it again because we were kind of hustling through it last time. How would I find this matrix? And by the way, of course, you know the result. So, well, anyway, I'll just do it like this. How do we understand this? How do we compute this matrix? Well, we compute it one column at a time. We take these vectors. We do the linear transformation to those input basis vectors, and then the result we write in the language of that basis. That's just our formula straight out of 5.3 of how to represent a linear transformation with respect to a basis. These calculations here are pretty straightforward. T of V1 is negative V1. That's the fact that this is an eigenvector kicking in. How nice, right? Lucky break. T of V1, easy formula to write down. And, well, then, I mean, here's a sort of a nice result from 5.3. How do you represent that image with respect to V? Well, we're representing an obvious linear combination of V1 and V2 with respect to V1 and V2. And so these coefficients are really easy to write down. This negative V1 is negative 1 V1 plus 0. Right? So this is our first column. And then analogously, because this is an eigenvector, T of V2 is 4V2, scalar being the eigenvalue. This linear combination, this evident linear combination of V1 and V2, how do I write that as a linear combination of V1 and V2? Well, it's observe. It already is, and just observe what those coefficients are. 4V2 is 0V1 plus 4V2. Again, a freebie, right? And so you can see the diagonalization happen by this becoming the first column, and this becoming the second column, and there it is, lo and behold, diagonal. Okay, so this is where we left off last time. And you might be thinking to yourself, well, is this a lucky break? Does this always work? Should it always work? Why does it always work if it does always work? So there's different points of view to take on this. I'm going to give you kind of several different points of view on this. You know, I think it's nice to have different ways of thinking about it. What made this work? Right? What really kind of made this work? How come this column ended up being whatever it has to be to make them, you know, to do its part of the task of making this matrix diagonal? Well, for this matrix to be diagonal, what you really need is to, within this column, have a non-zero entry only in the first spot. Right? Okay, so why did there end up being a non-zero entry only in the first spot? Well, we got that non-zero entry only in the first spot because T of V1 is a multiple of only V1. Right? First position here, non-zero number in the first position there, because the image is a straight multiple of the first basis vector. So in other words, the sort of the diagonal effect in the first column is immediately a consequence of the fact that that is an eigenvector. direct consequence, right? And then likewise for the second column. You know, what had to happen in this second column? How did this second column contribute to the, doing its share of making this matrix a diagonal matrix? Well, we needed to have a non-zero entry only in the second position. That happened because this T of V2 is a multiple of only the second basis vector. In other words, that happened immediately as a consequence of the fact that that vector is an eigenvector. So I hope this point of view is actually pretty kind of plausible and persuasive that, this is not a coincidence. They're not just sort of, oh, hey, what are the odds, right? If you make up a basis of Rn consisting of eigenvectors, all of them eigenvectors, they don't have to have the same eigenvalues. Just as long as they're all eigenvectors, if you make a basis consisting exclusively of eigenvectors, then this is going to be diagonal. So it seems, right? Just from the pattern. Now, here's a different point of view. What's the sort of the conjugation point of view on this? Notice here we wrote T, we did the translation. We wrote T with respect to the script V basis, not immediately by conjugating, but by computing those columns one at a time. Here's the conjugation point of view. The original matrix, change of basis into a diagonal matrix by, here's the new basis. Script V, basis of eigenvectors, is our new basis. Well, that means that is a basis of eigenvectors, which means these columns are eigenvectors. Right? And then, of course, likewise, this, of course, it's a change of basis in the other direction. So it's the inverse matrix of what I have over here on the right, but representing it as I have here, the columns of, the inverse matrix of the matrix on the left, again, are the eigenvectors. And then let's see, what about the diagonal matrix? What's going on over here with the diagonal matrix? What are these values here? Where did these values come from? Well, those values, trace it back, those values came from those values, which came from those values, which were and always will be these values. They are the eigenvalues. So, neat fact. And by the way, this is just, my intention here is to make it look kind of plausible, so you can see how the mechanics, how the nitty gritty sort of works out. This is not very good way to do a proof. We'll do a proof on the next page, next 2 pages, actually. But nice thing to remember, if you want to diagonalize a matrix, you have an undiagonalized matrix, you want to diagonalize it, do a change of basis, use as your basis a basis of eigenvectors that will diagonalize, and the diagonal entries will be the eigenvalues. And I think this arithmetic is pretty plausible that this should, morally feels like it should always work out. Okay, how are we doing? Everybody on board with our suspicion here that this kind of ought to work out? Okay. Now, I'm going to show you a couple of proofs that this, I'm going to say, does always work out. There is an asterisk that I've been sweeping under the rug here. So here's a theorem. A matrix is diagonalizable if and only if something that's not always true. But if it is, then the matrix is diagonalizable. The other side of this statement is that there needs to be a basis for Rn consisting entirely of eigenvectors. And now, sadly, we know that this is not always the case. Right? We saw back in section 5.4, we saw a matrix, a 2 by 2 matrix, a relatively harmless, simple-looking 2x2 matrix that only had one eigenvector. Grand total, I mean, again, it's not that we haven't found the other one yet. It doesn't have another eigenvector. So this will not always be true. Sometimes there are not enough eigenvectors to make up a basis for Rn consisting of eigenvectors. But if there is, the matrix is diagonalizable, and vice versa. And this is what I claim as we were noticing the pattern on this previous page. But let me give you a general proof of this fact. And I'm going to start by scratching off the sort of the punchline here. So let's not assume anything we shouldn't assume. Okay, so we'll start with, suppose the matrix is diagonalizable. This is what diagonalizable means. Right, straight out from the definition. A matrix is diagonalizable if that matrix is conjugate. Notice these matrices here are inverses of each other. If the matrix is conjugate to a diagonal matrix, what I have on the left here is a generic diagonal matrix, all zeros except for some numbers on the diagonal, about which I make no assumptions right at the moment, right? But some numbers on the diagonal. Straight out of the definition. And there's a very elegant and quick little bit of algebra that you can do to get down to the punchline. All we're going to do from this definition of diagonalizability is we're going to take this, we're going to take that matrix there, whatever that is, and we're going to whip it around over to the other side. Okay, so effectively we're going to left multiply both sides of the equation by this matrix, right? No big deal. Simple little bit of algebra. Then I'm going to flash back to chapter 1. Right? How do you multiply matrices? Here we have, you'll notice, a matrix, some matrix on the left, diagonal matrix on the right. A product has columns that are linear combinations of the columns of the matrix on the left, where I use the corresponding columns of the matrix on the right as my coefficients, right? So, for example, this right here is that linear combination. Oh, hang on. That linear combination of those vectors, right? These this column here, lambda 1 in the first position, all zeros underneath it, because this is a diagonal matrix by assumption. That linear combination of the vectors v1 through vn, well, we get lambda 1 v1, and then a bunch of zeros times the other vectors, so that all disappears, goes away. And we get just lambda 1 v1. Likewise, etc., etc. Where does this last column come from? Well, it's this linear combination of the columns of the left matrix. And so, well, these columns are mostly zeros. So I have 0 v1 plus 0 v2 plus 0 v3, etc., etc., etc. A bunch of zeros until in the very last term I have lambda n times vn. And thus this. Okay, so nice punchline. What I have here is a matrix whose columns look a lot like these columns, just sort of correspondingly multiplied by these diagonal entries, lambda 1 through lambda n. Okay, and so look at our last, the last thing we have here is this equation, and this actually tells us, suitably interpreted, this tells us that these column vectors v1 through vn are all eigenvectors. Think about, again, the same point of view, what does this multiplication say? Well, this times that gives you that, which tells you AV1 is lambda 1 V1, which tells you V1 is an eigenvector with eigenvalue lambda 1. And etc. V2, A times V2, well, is lambda 2 V2, etc., etc. A times Vn is lambda n Vn, so Vn is an eigenvector. Okay. Whoopsie, hang on. I wanted to delete. Okay, all right. All right, so therefore, these vectors, V1 through Vn, the columns, you'll notice, the columns of an invertible matrix, therefore a basis, those vectors are all eigenvectors. So this proves our result. What we were supposed to show is that diagonalizability shows you have a basis of eigenvectors. We're supposed to show purple implies green. Well, there's the definite purple. I have circled right there the equation defining the purple statement, and this is the after a fashion the definition of the green statement. So purple clearly implies green in two simple little bits of algebra: left multiply and interpret the products appropriately. Interpret the products column-wise. Everybody see this argument? It's a really elegant argument. And again, nice punchlines now. These are the eigenvectors. We can now conclude these are the eigenvalues. Right? These diagonal entries are these eigenvalues that you can see right there. Let me take a pause here for questions. Anybody? I think this is my favorite proof of this fact. Let me re-emphasize the fact itself. Diagonalizability, not always possible. Not saying every matrix is diagonalizable. But I am saying that if you can do this, if you can find a bunch of eigenvectors, if you can find enough eigenvectors, if you can make a basis for Rn out of the eigenvectors that you found, not only does that mean that the matrix is diagonalizable, but those eigenvectors tell you how to diagonalize the matrix. Okay. All right. Now I'm going to give you a different proof of this fact. This is a different point of view. By the way, neither one of these is in the book. So anyway, but I like this second point of view also. It's depends on your point of view. There's a way of saying that maybe this is even easier. But this is also a little trickier. So let me go through this. Here's what diagonalizability means. Diagonalizability means that we can represent the linear transformation T, same linear transformation T, just with respect to a different basis, as a diagonal matrix. Right? This D here, diagonal. Okay, so this will be our starting point. Instead of, what we started with over here was let's interpret it as being conjugate to a diagonal matrix. Here we're viewing it as, from a change of basis point of view, can be made diagonal. This just says what diagonalizability means. Okay, where can we go with this? What can I do, given that this D matrix, there's this basis script V. I don't know what this script V basis is. Still yet to be determined what these vectors are. But what do I know about D? And good news, I know a lot about D. I know D's eigenvectors and eigenvalues because D is diagonal. Right? We went through this last time, I guess it was. One of the really nice things about diagonal matrices is their eigenvectors and their eigenvalues are pretty straightforward, evident. Right? Whatever these diagonal entries are the eigenvalues, and whatever these the standard basis vectors are always the eigenvectors. Okay. So I hope everybody remembers this fact in green. Diagonal matrices, easy eigenvectors, easy eigenvalues. Yeah?
Wouldn't that matrix be the identity matrix? The matrix that you're saying is a vector?
Say it one more time.
My bad. So you're saying like the individual columns of the this identity matrix that you get from factoring out the eigenvalues?
I'm not sure what identity matrix is.
So sorry. What is that like? What is that matrix representing? Like next to the.
You talking about the D matrix up there?
No, the lambda I.
Oh, this is a scalar.
Yeah, and then what's the matrix?
This is a standard basis vector. So this is an eigenvector of D.
That just has a 1.
It's just it's a standard basis vector. Remember, so nice fact about diagonal matrices: the eigenvectors are always standard basis vectors. If this were Math 212, we'd be saying I, J, and K. Standard basis vectors are just vectors whose coordinates are mostly zeros, but with a 1 in a single position. Yeah. So all I'm saying here is that the eigenvectors are these easy to write down vectors. Okay. Yeah. Cool. That looks like is that a no? Okay. All right. Yeah. No worries. Okay. Okay. So what does this buy me? How does this tell me something about this purple basis? And I claim that this statement here is actually screaming something about the purple basis. It's just screaming about the purple basis in the wrong language. All right. So you may recall a while ago I made this observation that it's very important to be able to to look at a statement and interpret appropriately. Identify what language is being spoken here, right, and then translate accordingly. So the way we do that, you'll notice, what is this D matrix? Oh, D is in the language of this V basis. Right? So that tells me when I write down a bunch of zeros with a 1 in a single position, really that's code, that's V language for a specific vector. Right? And we just have to interpret in V language to figure out what vector is that really talking about. Well, let's think it through. If that is V language for something, then I'm asking the question, what vector is it? Here, I'll do this in purple. What vector is it that when I write it as a linear combination of V1 through Vn has coefficients that are mostly zeros with a 1 in that single position? What is this vector? Whose coordinates with respect to the script V basis are mostly zeros with a 1 in the ith position? Well, VI. Right? VI is that vector. So, VI is the vector that's being described here in the script V language with these numbers, that are again mostly zeros. Likewise on the other side of the equation. So what we see then, again, interpreting appropriately, this statement seemingly about standard basis vectors, well, that's, in the language of the script V basis, but that's really making a statement about these VI vectors. It's really making a statement about those vectors. What it's telling you is that those vectors are eigenvectors. Right? That's what this equation says, right? That these vectors are eigenvalues of that linear transformation, or if you want to talk in the language of the standard basis, they're eigenvectors of the original matrix A. So again, you can kind of different people have different feelings about this point of view. Is this proof easier or harder? There's a point of view that says kind of nothing happened in this proof. I made this obvious assertion about the eigenvectors of the diagonal matrix. That's old news. That's the result of a theorem that we wrote down last time. And then just observed that is the answer that I was looking for. Just in this different language, and that interpreted appropriately, it is more literally the statement that I'm looking for. And so I have a basis of eigenvectors. So again, starting with diagonalizability, we proved we have a basis of eigenvectors. Take your pick as to which one of these you like better, which proof you like better. I think the ideal is to consider both of these proofs as opportunities to kind of get some practice thinking about how to use these tools in different ways. So I encourage you to try to understand both of these proofs. But if you find yourself preferring one over the other, I totally get it. Okay, so here's kind of a summary page. Here's what diagonalizability looks like. Remember, diagonalizable means conjugate to a diagonal matrix, and that you can see the conjugate to a diagonal matrix in either of these two ways. These two purple equations, of course, both say the same thing. Now, this P matrix, we've talked about this on the previous, I guess it was last time, but this P matrix is a change of basis matrix. Right? That's the sort of the change of basis perspective on conjugation. Conjugations are a change of basis, and therefore the individual matrices are change of basis matrices. So that P is change of basis from B to S. Right? Which means, of course, that this new basis, which we know is a basis of eigenvectors, is going to show up as the columns of that change of basis matrix. Okay, so this relationship will always hold. Diagonalizability is always about a conjugation, or it's always about a change of basis for the linear transformation, and the change of basis matrix has columns that are eigenvectors. It's always going to work out if there is a basis of eigenvectors. And again, just to hit it, I don't want to make the mistake of, saying the word always too much and therefore sort of sweeping under the rug the bad news that, well, sometimes there is no basis of eigenvectors. Don't forget, sometimes there is no basis of eigenvectors. If there is, great, this always works. If there isn't, and there often isn't, then none of this works. Right? If there is no basis of eigenvectors, neither of the two constructions that we just talked about works. The matrix is not diagonalizable. Okay. Alrighty. Students very often have issues remembering, which one is the inverse? I mean, so the P inverse is on the left over here, and the P inverse is on the right over here. How do you remember? Is it on the left or is it on the right? And you can straight rote memorize that. That's one way to go. The problem is that this arrangement of it's on the left over here, it's on the right over here is only if your P matrix is the change of basis from B to S. What if you're looking at a question where you have this change of basis matrix? Maybe it's not called P. Maybe it's called Q instead of P. And maybe for reasons that make sense in that context, maybe it's not change of basis from B to S. Maybe for whatever reason the matrix you're given is change of basis from S to B. And then, I guess you could rote memorize, in this case, these are the two, and in this other case, it's the other way, and it switches because of the, oh my gosh, you're going to totally forget that someday, right? You might be able to memorize your way through of doing that all the way through this course, right? But 10 years from now, you will forget that. Okay, so what I would prefer for you to do is think it through. It turns out that unavoidably, it kind of has to be on one side or the other. So here's the way you can think it through. Your matrix that you're trying to diagonalize, naturally you view that as with respect to the standard basis. The diagonal form is, of course, what you get when you think about that same transformation with respect to a different basis. And notice, for this to be a change of basis equation, the bases have to match up. So whatever is there kind of has to be there, and whatever is, colors, whatever is here kind of has to be there, and whatever is, here, let me get rid of those. Whatever is here has to be there, and whatever is here has to be there. That's just how, the Legos have to fit together, right? So making that observation, there's really no choice as to where the inverse goes. This has to be S. This has to be S. That has to be V. That has to be V. And therefore, that one is P. Right? Or, oh, hey, if it's, if the change of basis matrix that you're given is given the other way, if it's, if it's given as change of basis from S to V, well, there it is. Right? And then that one is your, I don't know, maybe you call it Q. The point is you can explicitly see, if you interpret this conjugation from a change of basis point of view, explicitly write out which bases go where, it is unavoidable which one's on which side. So, as y'all recall, I have some additional homework questions, right, on the syllabus. They're not all taken out of the book. A few of the homework questions I've deliberately written in such a way that force you to figure it out from this point of view as to which one goes which way, and this change of basis matrix is the opposite of that change of basis matrix. Just think it through like this. Okay. Alrighty. So, how do you tell if you can find such a basis? I mean, we know diagonalizability is synonymous with there is a basis of Rn consisting of just eigenvectors. Well, how do you know if there is a basis for Rn consisting of just eigenvectors? We have to have enough eigenvectors. Right? There's also the question of independence. If you find a bunch of eigenvectors for one eigenvalue, and then you find a bunch of eigenvectors for another eigenvalue, we always find linearly independent sets, right? Well, how do I know that this linearly independent set of eigenvectors and this linearly independent set of eigenvectors, well, these are independent of each other, these are independent of each other. How do I know that the complete collection as a whole is still independent? It's not immediately obvious. The book gives a proof of this. You're not responsible for this proof. It's just details. If you're curious, you can totally read it. It's not a hard proof. It's just got some details in it. But punchline, this never is a problem. If you find a basis of eigenvectors for one eigenvalue, another basis of eigenvectors for a different eigenvalue, when you bring them all together, always independent. No problem along those lines will ever happen. Okay, so independence is not a problem. The only question is, do we have enough eigenvectors? Don't forget this little arithmetic, right? That in the number of eigenvectors we need, right? Well, that n is the sum of the multiplicities. The multiplicities are always at least as big as the number of eigenvectors, and so therefore, the best case grand total number of eigenvectors that I find, best case, is that we have barely enough eigenvectors to make a basis. Another way to say that is the only way that it actually works is if we never fall short. What we need is for every single eigenvalue, I need to have maximum possible number of eigenvectors. For every eigenvalue, you need the number of eigenvectors to fully equal to the multiplicity. Okay, so a couple of quick examples. Recall the first matrix we talked about, the characteristic polynomial, was like this. Those multiplicities, those multiplicities there are both 1. So what we need, fingers crossed, in order for that matrix to be diagonalizable, for the first eigenvalue, I'd better get 1 eigenvector. And for the second eigenvalue, I'd better get 1 eigenvector. And we did. Right? We got one eigenvector for the first one, and we got 1 eigenvector for the second one. Right? All the arithmetic and details are in that first example from 5.4. Okay, so that matrix is diagonalizable, and of course we already saw that diagonalization happen. Recall this little landmine matrix here. Innocent, harmless looking matrix that has something really terrible about it, right? I mean, tragically terrible. Oh man, in ways that you're going to see how tragic this is when we get into chapter 6. This is such a sad story with this matrix. Innocent seeming, and there's the characteristic polynomial, and notice the multiplicity of that lone eigenvalue. That multiplicity is 2. So for this to be diagonalizable, per the argument on the previous page, I would need for this eigenvalue to give me full-on 2 eigenvectors. But it didn't. Right, the tragedy that we saw there, and not clear how bad news that is, but we only got 1 eigenvector. At the time, it just seemed like, weird. How unexpected. But the result of that, the result of there being not enough eigenvectors as you would expect for that eigenvalue, is that matrix is not diagonalizable. So there is nothing you can do. There is no tricky conjugation that you just haven't thought of yet that will diagonalize that matrix. Cannot be done. And again, that's going to make for a sad differential equation in chapter 6. Okay. All right. So I'm going to very quickly show you some applications of these are the quick. Not such a huge deal, but nevertheless, kind of neato applications of diagonalizability. Again, the big application is going to come in chapter 6 when we can start killing some differential equations. But let's start with something more immediately accessible. Suppose I want to raise this matrix to a high power. And by which I mean, maybe I want to raise that to the power of I don't mean like to the 7th power, but what if I want to raise that to the power of a billion? And you might think, you know what, I'm going to go ahead and use a computer for that. Okay, sure, the computer can do that. A billion calculations, it's a lot, but it can totally do it. But it's a pretty inelegant way to answer the question, right? So let me show you a way you can do this by hand. We could raise that matrix to the power of a billion without just sort of tediously crunching through it, as follows. First, recall that it's diagonalizable. Right, this matrix has eigenvectors and eigenvalues, and we've seen how how knowing the eigenvectors and eigenvalues allows you to diagonalize, and diagonalization means this. Okay. Alrighty. Well, that also means this. Right? If D is a conjugate of A, then A is this sort of other conjugate of D. And that means that when I want to, for example, suppose I want to square A, I want to take this A and multiply it by itself, right, to square it. Notice that we end up with a P inverse right next to a P, and those cancel. And all I end up with is just a D next to a D, namely a D squared. So, nice little punchline. If two matrices are conjugate to each other, their powers are correspondingly conjugate to each other, right? So A squared is conjugate to D squared. And in a very, I almost said similar, in a very analogous way, A cubed is a conjugate of D cubed. And A to the power of a billion is a conjugate in exactly this way of D to the power of a billion. And the nice thing about that is diagonal matrices are really easy to raise to high powers. Right? There's nothing tricky about how you multiply a diagonal matrix times itself. You just raise the diagonal entries to those powers. Okay. So, -1 to the power of a billion. Easy. 1. Right? Right? 4 to the power of a billion. Well, it's a big number, right? But nevertheless, I understand that number extremely well. 4 to the power of a billion. 2 to the power of 2 billion. It's a number I can write down and immediately understand. And so, notice then that the punchline is this process of trying to understand, what would otherwise be very kind of brute force clunky arithmetic boils down to an easy matrix, even after being raised to the hugest power you can think of. And then, well, I've got to do this one little conjugation, and that's it. Very cool. All right. I want to show you an application of this idea. This one is really just kind of because it works and it's kind of neato. I'm not aware of any engineering applications of this, but a lot of y'all might have heard of Fibonacci numbers. Have y'all heard of Fibonacci numbers? Okay. So there's a lot of neat facts about Fibonacci numbers. If you haven't heard of these before, then here's kind of the first sequence, and the relationship between Fibonacci numbers is typically presented as, a given Fibonacci number is the sum of the two previous numbers. And once you've decided that you're going to start with 0 and 1, well, that means that the next number has to be the sum of those, which is 1. And then after that, the next number has to be 2. And after that, the next number has to be 3. Seems like a pretty boring sequence. But then this next number, that's 5. And then the next number after that is 8. And then 13. Okay, it's hard to tell exactly, where is this going? Okay. So, question, what is is there a formula for the nth Fibonacci number? This is a recursion relation. But if I just want to know what is the 1 billionth Fibonacci number, right? Do I have to, I guess I could write a little computer program and brute force crunch it out. But again, inelegant. Okay, so very often in math, it turns out that the way to solve a hard problem is to rephrase it as a harder problem. It's weird, but that works surprisingly often. So what I'm going to do is make this observation that this recursion relation between individual Fibonacci numbers, notice that all that is sort of the first line, if you will, of this matrix equation. Notice that the second line of this matrix equation just says Fn is equal to Fn. And so, I can think of this recursion relation between Fibonacci numbers as being a relationship as a sort of a recursion relation between consecutive pairs of Fibonacci numbers. Right? If you know a consecutive pair, like, the 2 and the 3 here, right, of Fibonacci numbers, and you want to know what's the next consecutive pair of Fibonacci numbers, they're related by a relationship, a matrix product. Okay, so again, we've successfully taken a hard question and made it look harder. Okay, now, why does this help? Right? Why does this help? Well, it depends on how you look at it. But one pretty good point of view on how this helps is we've turned an addition into a multiplication. How about that? Right? But more to the point, we have turned this question of, what is the nth Fibonacci number into what happens when I start with the, this, you might say, first consecutive pair, and what happens when I apply this relationship here, the sort of the thing that moves me over one notch at a time. What happens when I do that in times? Well, I'm going to get over to that consecutive pair of Fibonacci numbers. And the nth Fibonacci number is the bottom element of this vector that results from multiplying this matrix to a high power, which we now know how to do, times that vector. So, neat fact then. What I have is I am now looking for, as you can see, I'm looking for the bottom entry in the vector that is the left column of a high power of this matrix. Right? Looking for the bottom left entry. So I just need to raise this matrix to a high power, look at the left column, look at the bottom entry in that left column, That's my answer. And the details, again, come from diagonalizing. I'll let you guys read through the details here, but this matrix has those eigenvalues and eigenvectors. Diagonalize, multiply it out, and here's your formula. I'll let you guys read through those details. If you have any questions, feel free to talk to me. Okay, see y'all later. Have a good weekend.